All right, we can go ahead and get started. So appreciate everybody for coming out. I'm Wilson, data scientist, been hosting our PyData meetups for a few years now. Today we have Josh McGraw. He's a software engineer and PhD candidate out of Indiana University over in, are you in Indianapolis right now, or are you
Bloomington right now?
Bloomington? Right. Gotcha. So yeah, he's been doing a lot of work in reinforcement learning. So our talk today will focus around reinforcement learning using Google Colab resources. So super excited to hear more about this topic specifically. So as far as announcements go, for anyone that wants to watch these videos after the fact or share them with your colleagues, they're available on the MetroStar site. This is a free and open event for anyone that wants to attend. So feel free to visit the MetroStar YouTube page if you'd like to take a look at this video afterwards. We have some open roles that are always good to make note of. Everything from AI/ML lead to full stack developer. If you're interested in seeing some more of these, we have plenty of them open. So for those that are unable to see the screen, there are roles open for AI/ML lead, senior data scientist, cloud security engineer, and senior full stack dev. So if you'd like to take a look at those, they're available on the MetroStar page as well. So with that being said, thank you to our sponsors, and that's NumFocus, the PyData group in general, and of course, MetroStar. So with that being said, I'm going to turn over screen control to Josh, and we can get started. One of these days I will figure out Zoom. There we go.
Hey, prepare.
All right, now Josh, you should be good.
It looks like it. Okay, how does this look?
Looks good.
We can see it.
Okay, great. Okay, so these are going to be a few slides. Actually, I'm going to start off with just to motivate exactly what I do, which sometimes I wonder myself. And so this is everything I can't fit in Google Colab. This is building a mind with Unity. And so mainly about myself, I just like building kind of deep RL agents. And so I've always had this passion for just finding a game that I like. And actually, this is a project I worked on Wilson with, so I had to include it. These are each just reinforcement learning agents in one game or another, one environment or another, all with varying sizes of action spaces and inputs as well. So in each of these cases, these are image input, image to decision. This is actually a ragdoll agent. I'll kind of go into why it's a chicken later on. I happen to work a lot with chickens here for reasons you probably won't be able to guess yet. A little bit of Super Smash Bros., one of my favorite games, and a RuneScape curiosity agent, which is curiosity is going to be a big theme of the talk here. So let me see what I can bring in next. More towards my PhD itself, we actually study, I'm in a lab that is called Building a Mind, and we actually study sort of what's called digital twin versions of cognitive tasks. So my major is interactive and intelligent systems with a secondary major in cognitive science. So often I'm comparing the models that we have for visual intelligence to models of actual biological intelligence. We're comparing them for sort of robustness and capability, biological plausibility as well. So here we have just an example of one of these digital twin experiments. This was for a paper that I recently had submitted to CogSci, and not the paper itself. The one on the left here, learned social preference in zebrafish, was the original study done in 2004. And this was just a study that showed that these wild type and albino zebrafish when raised together, showed certain types of social preferences, and when they were raised separately, had a completely different type of social preferences. Specifically, the agents were more likely to associate with the types that they had seen when they were being raised. And so our question was, can we recreate this in machines? And what is the minimal number of pieces that we would need to make that happen? So we hypothesized it was probably just going to be intrinsic motivation and reinforcement learning. The reason that it's important to find what's sufficient here is because there's, of course, many ways you can get biological seeming behavior out of agents, but we wanted one that first included an intrinsic motivation. In this case, we used curiosity. We actually also tested a few other forms of intrinsic motivation. And if you're not familiar with RL or reinforcement learning in general, usually you will describe an explicit reward structure for your agent. In cases where that reward might be very sparse or difficult to actually attribute to certain states, you can use what's called an intrinsic motivation, and this just gives the agent some type of reward structure that isn't entirely based on being hand-fed. So these agents were only motivated by curiosity, no extrinsic rewards, and given reinforcement learning. And so what we did was we set up the same type of experiment. We placed these two fish, these orange and then blue, and we just put them in the same environment, raised them independently, and then brought them back together and saw what type of behavior they would have. So the two tests here were essentially, one was called a two alternative force choice task. This is pretty common in psychological literature. In cases where you have just two types of classes of outputs, you might do a two alternative force choice task. So this kind of lends itself from cognitive literature. I'll play this and I'll show you. So this agent here actually was raised only ever seeing other orange clownfish. And so replicating everything in the study down to a T, this box chamber that they're in is actually the exact same dimensions as what the original study by Essinger 2004 had. So we map out the exact same dimensions, the same training conditions as well. So although I didn't show it, they were trained in a 100 milliliter size cup and for about the same duration. So this fish, if I were to just keep playing, and I think it goes on for about 5 minutes here, I won't subject you to that, will almost always just prefer to see this familiar stimuli, even though it was trained with curiosity. And I'll talk a little bit more about how curiosity is formulated and why this would happen. You might expect that it's curiosity and it's looking for novelty that it would go to the other group. But the reason that that doesn't happen is because we have two systems that are going on during reinforcement learning. We have the policy, which in this case was controlled by PPO, proximal policy optimization, and we have curiosity. Curiosity is a reward just for novelty. And so you can formulate that in dozens of ways. But the way that this gets done is a prediction. And so the agent needs to predict what the next time step will look like given its current action. And then PPO is trying to modify the policy to get the greatest amount of reward while changing only a small amount at a time. Curiosity, because there's many ways to be surprised as a new agent, initially starts out quite high and the agent is unable to predict, or at least part of the curiosity module cannot predict, but over time it will learn to predict. In which case those trajectories and those decisions become less prevalent. The agent stops exploring those options. What happens here is that training does eventually taper off in the same way that learning sort of has a critical period in biological intelligence. although there's still lifelong learning. It's not to say that we stop learning really at any point, but there are certain periods where learning really kicks in. And in this case here, the development of early stages of life are especially one of those. So I haven't even reached the point where I've described ML agents, but underlying all of this work really is ML agents, which is the platform that performs all of this reinforcement learning through Unity. So I'll show you now what happens. Actually, I'd like to show the isolated group first. So these were fish which were isolated during training. I'll actually open this up. Yeah, feel free to put questions and I can actually answer them right away, or unmute yourself and just ask. I'm fine with either one. So these agents have really never seen any other fish before. They still had curiosity, but they were raised in a pretty much empty, featureless environment. So what you get is kind of this boring, not very plausible behavior. They really just scatter around. Here's what happens when you have these fish which have been trained in groups. Mostly the only thing that's left in the environment to be curious about by the time that training has ended are the other fish. And that tends to always be the case. We tend to find people more interesting because people are unpredictable and people tend to remain unpredictable. If you were to model your way around a 3D physical space, then your walls are pretty consistently always there. Your chair and your table are always there. Most things are sort of stationary. Most things, and as far as you need to embed them, are quite stationary in some high dimensional space. It's the social interactions, which are almost completely unpredictable. They're much higher dimensional, and you need a lot more data to actually model that. And so that's why curiosity can remain for so long when it's in terms of social agents. And that's sort of also why we had formulated this to begin with, of course. So we kind of had a guess going in that it would somewhat validate our hypothesis. We'd seen this before, sort of with some other types of agents that we had. So on the left here are the chickens again. This is the same model, same different set of training data, which of course, as we can demonstrate, the training data is quite important. When you're considering a reinforcement learning agent who is learning online and has to learn from their own experiences, poor experiences lead to bad policies, lead to bad models, lead to even worse policies, lead to catastrophic failure in terms of learning. So a good policy and a good reward structure tends to be a very sensitive component of having your reinforcement agents learn. So on the left here, just a ton of chickens, essentially all following each other around. And if you've ever seen chickens run around in little playpens, this is kind of exactly what they do. They just follow each other around. They like doing that. On the right, we have some bees, and this was for a little project kind of on bee vision and bee collective behavior. Bees, of course, have an incredible sense of collective behavior. They even have this little waggle dance that they will do to specify the exact angle, direction, and position of food sources. So if you've never seen the way that bees communicate to their hive, I highly recommend looking it up. I can't show you here. I just don't have anything really to show you about it, but these are two types of collective behavior. So collective behavior actually exists almost everywhere that we look at it. Certainly among fish, among birds, among insects. And so could we model something as simple as a chicken brain? And so that's kind of where our research leads, is these are pretty simple model organisms, right? And they're just chickens or they're just bees. Are our best vision models capable of replicating this? And so that's our question. Are the field's best models smarter than newborn chickens? And there is a reason we use newborn chickens in our experiments. We actually collect our own benchmarks as well. So the study I mentioned before was Essinger's 2004 study on zebrafish. We have over a decade of benchmark data of chickens And the reason we use chickens is because when they have similar homologous cortical circuits to humans, meaning they have the same series of pathways along their visual cortex, going from V1 to V2. And the other reason is that they are precocial species, which means that they actually run around from day one. They don't need their a parent to really nurture them, besides being hatched and having the eggs stay warm. But that we can incubate. So what we do and what I've been spending a lot of my PhD working on is this specific setup of a 4-screen virtual reality chamber. And the reason that we use virtual reality is because we can pretty much show any type of experience to these chickens. It's 24/7. We can design any type of cognitive task that we'd like to do. Chickens also have this really nice advantage in terms of research, in that usually you would reward the agent or the animal just with either food or some other type of stimulus that they like. Chickens happen to imprint very quickly to whatever they see, and so you can imprint them to some type of what we call the ship object. And I think I will have an image of it. It looks like the Starship Enterprise, if you've ever seen one. But it's red. They really like this object, and so they'll spend most of their time next to these monitors which are displaying that object. And that ends up being a way that we can measure whether or not they can recognize this object from, for instance, distractor objects which might look similar but are not the same object. And in fact, you can show the chick just a few degrees angle rotation of an object, and it will be able to form view invariant recognition of that object. That's something that most computer vision systems, even now, are not that capable of. However, I think with research in things like nerfs, we've seen that you can get a pretty good collection, and it would be interesting to study it from a cognitive standpoint, how it relates to the brain. What happens when you see just a few angles of an object? Can you recognize that object from the other side? It seems trivial to us, of course, but we have decades, of course, or more of experience with vision. These are the chick's very, very first experiences with any type of sensory experience. Arguably, this gets to the core of nature versus nurture. What type of data do you actually need to train your algorithms? In our case, we're considering biological algorithms. So this is part of the chamber that I had built. What you see here is actually a hamster in the center. Her name is Dr. Lee, and she is controlling a virtual mouse. Overlaid on this is actually a Unity scene, which is tracking her position and updating this viewpoint here as if she is the controller. What also happens in this scene, and it's very important for actually the VR perspective, is that you need to project these monitors specifically for the viewpoint of the animal. And that's why we need to track the position and the head position of the animal. Because as you can imagine, if you try doing this, if you got some hands free, putting your hand up and then looking through it, you get a different angle as you move your head around, but that's not going to be the case if you are looking at just a flat screen. As you move around your flat screen, all you get is a warped projection. So what you need to do is invert that projection and create the VR effect. And so what it essentially becomes is like a window. It's the same way as when you look out a window, you can move your head left and right, you can see more or less information. And the same type of VR effect is done for humans in a system called the Cave, where it's 4 projectors on a wall. It tracks your head position and then updates the projections as they are. But the only limitation of this is that you are physically limited to a 10 minutes. We'll see. Do you get that message, Wilson?
No, I don't see anything.
Okay, I got a message that said I had 10 minutes.
No, you should be fine.
Okay. Nonetheless, The limitation of this box is sort of that you can't move outside, in like in traditional VR, you could just move somebody to any space. This really kind of works like a glass box. That's okay, because in a lot of these experiments, you don't need that much stimulus. You don't need them running around that far. And so then you might even ask, why would you put animals in VR? And the answer is because we can build impossible worlds, and we also have incredibly precise replication. So we can use the exact Unity environments that were projected on the screen and then just host an RL agent in them in silico. So this is an example of one of these chambers, what it would be like for an AI agent. You can kind of notice the projection warping that occurs here, and it's pretty obvious here if you look at the sun. Down here, it will look perfectly fine, but from this perspective, it needs to be inversed. The projective matrix needs to actually be inversed so that it takes into account the position of the viewer. It also means you can only place one agent at a time in here, since there's kind of a sweet spot for the perceptual effect to occur. But as you can see, we can generate all different types of virtual environments to place these chickens in, and there's essentially no limit to it. We can generate types of visual illusions, which of course are incredibly insightful for understanding our own natural vision, because we can understand what types of things our brain is pre-processing on our data. Okay, so that's good. We have about 30 minutes. And so I'd like to actually go over to Google Colab. And as Richard Feynman once said, what I cannot create, I do not understand. So let's take a look at the Google Colab. I'd actually like to share this document too, so I'll be placing it in the chat. What I'll do is we're going to describe actually how to build your own ML agent, what it takes to do it. And hopefully I can get through this in the right type of order. It's kind of difficult, but it is a Python notebook, so you can always go back through it. I use Colab Pro because in this case here, we're training deep neural networks, but we're also training deep neural networks which are receiving vision as their input. So we definitely need a GPU here. I don't know what to tell you if you want to use your CPU. So let's get started. All we have to do here first is kind of prepare the Colab environment. I'll actually mention I don't usually train these agents in Colab. The reason is that we have servers in our lab that we run this on, but I think that it's just kind of a very novel and at the same time very scientific way to run these experiments, because you can clearly just save or share these notebooks with other people. And until now, and actually until recently, this was something I'd never done before. In fact, nobody in my lab had done this, getting a full pipeline set up from running training and performing analysis all in one notebook. Usually it's kind of a painful process. I don't want to turn anyone off from ML agents too much, but it's a little bit of a painful process at first. There's a lot of things that need to be moved between your server back to your local environment with the Unity editor, and then rebuilt, reshipped, and then rerun. This just seems like a much faster and easier way to do it. So if you've got it open, or if you want to follow along, I'm going to change the runtime type to make sure I have at least a GPU selected. Colab doesn't like changing the Python version, so we kind of have this hacky fix that we found, which let's just get around that. Essentially, we're just going to install Miniconda and change some links. So I'm going to run the first cell here. ML Agents has 3 parts in the Python side of it alone. There's ML Agents environments, which just allows for the low-level interaction with the Unity environment. You could technically create your own trainer using PyTorch if you wanted, and then you would be using the ML Agents in package. There's ML Agents just ML agents as a Python package, which is a higher level library, includes a few off-the-shelf reinforcement learning algorithms like PPO and SAC, and it does the communication between the Unity executable and Python. Then we just have the ML agents learn executable, which is what we're going to run in the console at some point. So this will take a little bit of time. And in the meantime, I think some people have probably heard, if you've heard about Unity, you've probably heard about it recently because of some of the bad press it's gotten. And I think it's worth mentioning that none of this really matters because, well, one of the reasons that it doesn't matter is this is only for if you have only over 200,000 installs. And in which case, congratulations. So I was just going to say, Unity's received a lot of bad press about this. It's really a monetization strategy that they've implemented, where they wanted to highlight that they actually have two products. Unity has the Unity engine and the Unity editor. If you write scripts, you're using the Unity editor. If you are running or installing a game, most people are using the Unity engine. That to me even wasn't a clear delineation until they made it clear, unfortunately, with a little bit of bad press in doing so. But as far as being a researcher goes, it doesn't really matter. You have to have a pretty high number of installs for this to really matter. So I don't want anybody who's heard about Unity let this poison the well at all. So we're still going on installing some of the requirements here. It's kind of goofy. ML Agents has its requirements that require you to downgrade some packages. But this cell will run everything you need. Since these agents are all visual agents, we also want to have an actual display. This is the hardest thing about running it on a server. ML Agents doesn't need to have a display. You could run all of this headless mode, but if you're running an agent that takes an actual camera and creates images, then Unity requires a display. And so what we'll do to get around this is usually create virtual displays. And so that's kind of what we do here. We import a virtual frame buffer. This lets us create a virtual display and essentially make it an output. We never have to look at it, but Unity at least has to have something so that its cameras can render. Since this is going to go for a little while. The way that this actually gets configured, if you are familiar with running any of these models, or you're familiar with PyTorch, you probably are pretty used to a low-level control over the models. And so what you get with ML Agents is a configuration file where you can describe some of the high-level architecture choices. But most of it is kind of out of the box. You can choose if you want your visual system to be a simple CNN, a ResNet, etc. You'll choose the policy. You'll choose some of the types of reward systems and give it the weights. You can still parameterize things like your epsilon and alpha values. But for the most part, you will be getting a configuration YAML file. So it's not exactly going to be run through PyTorch, though it does initialize a PyTorch run. That all happens on the back end. I think the reason they do that is they want it to be pretty accessible. And so nonetheless, it's when you have something like of outcome. So I'll state that again. Forward model predicts the action or predicts the outcome of an action. Inverse model masks that action and then says what action resulted in this state. If from state 1 to state 2, what action did you take to get there? And that's necessary because if you're just looking at a purely surprisal-based intrinsic motivational system, you could just have stochastic noise and the agent would love that. And the reason is because there's nothing, it's always surprised. It can never predict what's happening on just a random TV screen. So this is actually called the noisy TV problem. It was pretty evident when you train early curiosity systems that if you just had any type of stochastic noise, the agents loved that. And so you needed this inverse model to say what part of this surprisal came from your own actions instead of just the environment. The environment will be surprising, but after a while, the agent learns to predict kind of this noisy TV, or at least learns that it's not associated with any action. It gets no reward because there's no correlation between what action it had and what the next frame of the TV was. So it eventually decreases the reward. That's how you get over this noisy TV problem. So in the environment that I had shown earlier, this is what the environment actually looks like. We have four agents and we get a different brain for each agent. The rewards are only curiosity and they have a discrete action space of 5, meaning they can move forward, they can choose not to move, they can rotate left, they can rotate right, or just not rotate. So at any given time step, they choose 2 of these. So they could move forward and then also turn left. They could rotate left and move forward. They will actually rotate before they move. That way they can make a left turn or such. This is what it would look like actually in Unity. And this is one of the components where you would just configure this option. So you can choose how many outputs this network has, and you can choose what to do with it. For discrete actions, kind of like a button press, you might set it up that way. Or if you have something that's continuously valued, you could create continuous action branches. And so maybe you'd like to control a steering wheel in some sort, and it might make sense to frame it as individual turns, but it might also make sense to have it as one continuous value. In our case here, it's just easier to assume that it's like a left button press moves them left, a right button press moves them right, and holding forward moves them forward. So this is actually going to download the file from Google Drive. And cross our fingers, this will say Unity. What I'm actually doing here is I'm creating that virtual display again. I'm running NVIDIA SMI just so that we can verify that we have a GPU. Here we have the Tesla V100. And then we're calling the main function here. This is mlagents-learn. Here's our configuration file, which I'll open up and show you what that actually looks like. We give it a run ID and a base port. It needs some type of communicator between Python and Unity, so it creates a little local TCP port for that. Inside here, which if you just were to download this, if you were to put this into your browser, you could download the zip itself, but it's nice just to have Google do this because it's their bandwidth, it's their gigabit bandwidth, so it'll download in seconds on their servers. There's no reason to really download it to your own computer, which is going to be slower, and then upload it back to Google Drive. By all means, you can do that if you want, but I find it to be a lot easier to just work within the runtime here by downloading it. So in here, we have a configuration.yaml file. I'm going to open it up, and it opens on the right side here. This is where we describe all of the trainer settings. We're going to use PPO, and then we can also describe the settings for this network. So a batch size of 256, buffer size of 2048. Here's our learning rate, the learning rate scheduler. And so this is how quickly does your learning rate fall off. All of this is just documented on their website pretty well. Unity ML Agents has a great set of documents online. One of the best, I would best documentations I've seen in a while. We can describe the number of layers. And so this at first kind of rubbed me the wrong way. I was also very used to doing things in like PyTorch, where the idea of just saying number of layers equals 3 was kind of strange, but it simplifies things. And you can also configure this. This is essentially a high-level wrapper for running some type of PyTorch model. You can configure this any way you'd like to. The YAML is just high-level wrapper. Here we can describe our curiosity signal as our reward signal. A gamma of 0.99 would be what strength is it? Well, you know what? I'd have to remember exactly what each of the parameters does, but none of us exactly remember. Too many parameters off the top of our head. But I believe that gamma would be the fall-off factor, how quickly that this curiosity will fade. The strength is just the overall strength of the reward signal. It only makes sense here because, well, a strength of 1 is fine. We have no other reward signals here. We could put extrinsic rewards, but these environments, of course, were not meant to have any extrinsic rewards, so there is no extrinsic value to even be shared with the agent. Past that, this is just a configuration file, but it's essentially going to have your typical hyperparameters that you might want to tune while you're training these agents. The nice thing about Google Colab is you can change any of these and then just save it. Here, for instance, I actually set it to be 1000 just so that we wouldn't start a train that was going to take too long. Even if we get some goofy agents when we train for only 1,000 steps, we'll get some brains. Hypothetically, and as I was telling Wilson a little before, having Colab cooperate with me is sometimes the hardest part. This is all correct, and if it had reached to the very end, which I had hoped it would immediately start downloading these .onx files. What we could do then is just open up Unity, go to the exact same scene, and instead of it saying no brains here, we would just drag in this .onx file. That would be the trained brain, and then it would start running in inference mode. At that point, we could start recording the position of the agents. For instance, that's what we do in these experiments. We would record the position of the agents and then look at their distance to their nearest neighbors. We would have other tabulated data like their orientation, whether they're a blue-orange fish or a blue clownfish or an orange clownfish. So I thought that the science side of this was really fun, but still, I just like building reinforcement learning agents. And so I built this environment a little earlier, and actually I built it a little while ago. This is one of my favorite because it mixes intrinsic rewards with extrinsic rewards and has a ton of other very cool features. It's actually like a space dodgeball. And I thought if I was going to leave this group with anything, it's going to be the source code to this environment. I can show you what it would look like to actually play it. And so these are not truly agents, but I needed a way to demonstrate what the game actually looks like. They essentially pass around this flaming dodgeball. They will reflect when it gets close, and in this case, they're all being assisted, so they just reflect at the exact right time. If it hits them and they're not reflecting, they explode. This is a pretty difficult task because, of course, they need to orient themselves. They have 2 camera sensors in front, and these camera sensors can also rotate. So they actually have to control the parity of their vision. And so that means that they are given the opportunity to build stereoscopic depth information, but they have to learn and train to do that. Yes, let's get back to the Colab notebook here. I'm going to do the same type of thing. This is also on Google Drive. And so we can pretty easily let Google download it itself into our runtime. And if I'm any luckier with this environment, this one will work. I think what happened is that between the different types of GPUs that Colab offers, some of them might play well with a virtual display or not. And oddly, I had this working yesterday, but Murphy's Law says that it can't work now. So up until now, I haven't actually shown the Unity editor because it's sort of an intense beast of its own. It's also mainly C#, and so might be either out of scope or not much of interest, but the project itself is available down here in the resources. So if you know how to use Unity, or you're interested in using Unity and you want to learn something about building ML agents, this is a great little practice scene that you can download. You know, it is still trying to train here, so that's why this cell hasn't started running. While we're attempting that, I think I will actually just show what it looks like to build and configure any of these actually in Unity. This is actually, I'm remoted into my lab PC here. This is the clownfish scene, and what we have here are our collection of objects. We can select any one of these agents here, and if I scroll down here, here is the screenshot that we actually had before showing their action space. I could select a model here, which you'll actually see I have many different types of models here that I've trained, each of these in different types of rearing conditions. So some of them have been trained with social partners, some have been trained without social partners, some of them are for brains of the orange fish, some are for brains of the blue fish, some are trained with curiosity, some are trained with other intrinsic motivation systems, which I didn't really have time to get into, some being like R&D, random network distillation. We have contrastive learning. We have curiosity with random features. These are all different types of ways that you can formulate intrinsic motivation in a system where there's not much explicit reward to be given to your agents. And in an environment like this, what explicit rewards are there to be had other than socialize in some sense? So we can configure each of these brains with whatever models you'd like, and when you hit run, it's going to just use these trained brains. These are .ONNX models, open neural network exchange format, and so these are exactly what you get when you finish running. Your results folder then just has a ton of .ONNX folders that are after the finished run. We can go back to just play this environment, and hopefully the brain sizes match up. I think they should. Here we go. So these are this is the behavior of these agents, for better or for worse. Some of these have extremely low values on their intrinsic curiosity. Some of these have been reared without any social experience. And so Maybe this is what we would expect to see in fish that were raised in exactly the same type of scenario. When we find these types of results, what we often like to do is find where the gap is. We have these models and we have the simulated behavior. So what are the gaps? And we actually need benchmarks to say that. We need to have benchmarks to know whether there are gaps in the behavior of these animals. And so anytime that we can find an experiment, or anytime that I can find an experiment in which we have very clear data about the behavior of an animal, for instance, shoaling fish, or even honeybees performing mathematical operations, which was a real paper. We go back and try to see if we can get an agent who has vision to accomplish the same tasks with some of the most state-of-the-art models. And so most recently, we've been moving into adding VITs to our systems, vision transformers. Those seem a lot more promising, but also don't share as much of the biological similarity as something like a CNN. And so all of these factors we keep in mind while we're in a search through the models, but most importantly, we always have the benchmarks so that we can say which of these models is most brain-like, is most biologically inspired. And then if we find a model that seems to be a good candidate model of biological intelligence, what we can do is put them in impossible worlds and then say, what would happen? Because now that these are models, they're also theories of the mind. We can use them to say, what would happen if we put a chicken in this experiment? We can first run the AI agent, then we can put an actual chick in that experience, and then we can compare which model did the model actually correctly predict it. If it did, then it still remains a good theory of the mind and of visual processing. So that's sort of the intended outcome of much of this research. Hopefully it has killed enough time since it began. And I think it's gonna run the same way. Unfortunately, this would be the type of error you would get if you don't have a virtual display running. And unfortunately, the suggestion that it gives of passing it with no graphics doesn't work, because, like I mentioned, Unity needs graphics in order to render cameras, which vision is specifically the input to these models. So I guess I know what I'm going to be doing tonight is fixing this up. If there's any questions, I'm happy to field them here at any time. If not, I can show a little bit of the other environment we had for the Genji ball, and possibly show some of the trained agents that have been built there in the meantime while people think about.
Definitely open to seeing trained space dodgeball players.
Yes. Yeah, the most fun part about it is I would train this and then I would stream it to Twitch as well, just so it would be an online stream where people could watch these agents learn. And most of these projects that are my own personal projects, I tend to stream to Twitch just for fun, because I think it's fun to tune in and watch these agents learning. So similarly here, I'll actually drop in this environment. Since I've given the link to download it, it would be useful for people to know how to use it. There is one prefab here, and prefabs are sort of pre-made sets of game objects that we can just drag into the scene. This is a player, and it's got its purple outline. The rest will be AI agents, which have a blue outline. So given that these are not actually I'm down here, I can control with the keyboard, and this is heuristic mode. This is a really useful way of testing your agents while they're training. You may want to sometimes just force actions onto the agent or otherwise change its action buffer by hand. So they're essentially brainless. They've got no brains. So all we'd have to do is assign some brains to them in the same way that we did before.
And these are using the prefabbed architectures provided in Unity, like you mentioned?
Yep. Yeah. So when I originally trained these, I gave it a split between 50% curiosity and 50% extrinsic reward. The reason being is that they should learn to map their own actions to their body. Since this is an embodied first-person view type of thing, it's important that the RL agent knows how to navigate its own environment. Curiosity does a great job of that. Sometimes so great, in fact, that my curious agents will escape from their containers. I mean, I've had a lot of curious agents, which, for better or worse, they want to explore kind of the edge cases of what's possible in their environment. And so very often you game designers will actually place curious agents inside of their games just to see if the agent will get somewhere that they didn't expect players to be able to get to. And that's a lot easier than having to pay game testers to repeatedly do some of the same actions. So another possible use of curious agents, we kind of don't like when that happens because it means they've jumped the gate and we got to herd them back in somehow. Okay, I think I got another 10-minute message, so I want to just kind of wrap up here instead. I can specifically take any questions or comments, or just tell me how your Halloween went.
I handed out Pokemon cards, so
That's a great idea.
yeah.
That's a really great idea. Yeah, I'm going to hand it back off to you, Wilson.
Sounds good. Well, appreciate you doing the talk, Josh. And yeah, I'm looking forward to trying out the, clownfish. Maybe I drop some krill in there and have a little
Absolutely.
adversarial action going on.
Yeah. Yep.
But yeah, if anybody's got questions, feel free to unmute or anything. Other than that, appreciate everybody coming out to the November Pi Data talk.